Good morning. First of all, I would like to thank Professors Tassignon and Palikaris for inviting me in this workshop. In the previous talks, and actually Dr. Guinness presented some computational measures to evaluate visual performance. This talk is more concentrated on some subjective measures, which are done through visual psychophysics. So the outline of this talk, first of all, I'll have a couple of slides on which factors limit the quality of vision. I will talk about visual acuity, although it's a simple test, as we all recognize. Maybe it's the standard and the most important, as is done in most ophthalmological routine, and we record with visual acuity, resolution, and recognition. I will talk about how important is contrast and how we can evaluate it through contrast sensitivity, and show some results from evaluating contrast sensitivity in the presence of ocular higher-order aberrations and some following refractive surgery. So what the field of psychophysics, which is not only belonging to vision but also in other senses, examine is the relationship between the physical stimuli in our environment and our responses and physiological reactions. So what an observer sees, hears, and reports. We have to realize that any examination of the eye or of the visual system consists of a series of psychophysical tests, such as the visual acuity, the evaluation of the refractive error, the visual fields, the color visual examination. And what actually visual psychophysicists do is they devise non-invasive procedures for, first of all, strengthening differential diagnosis of the diseases, monitoring therapy of the diseases by evaluating the effectiveness of treatment, pharmacological treatment or surgical treatment, and also developing some screen text for high-skill tasks such as driving a car or flying an aircraft. Probably you've been through this before, so I go very quickly. I mean, what limits the visual quality and actually the image, the retinal quality of the image, is first of all the sphericylindrical error, sphere and astigmatism. However, as it has been known now for some decades, there are some other factors like the higher order aberrations and scatter, which limit quality, and these usually come from the ocular surface of the cornea and of the crystalline lens. Moreover, as it's shown in the first talk, diffraction is one factor that limits visual quality, but this, in the case of the visual system, is more like theoretical, because what diffraction says is the larger the pupil size, the better the visual quality. However, due to the existence of higher-order aberrations, we know that the larger the pupil size, the bigger the effect of aberrations on the visual quality. So there is a counteracting effect here, and probably diffraction does not limit visual quality a lot. And we have to realize, because we speak about a system that contains neurons, that the visual quality also is limited by the photoreceptors, which are the cones that function during lighting and the rods that function during low light conditions. And we have to remember that cones have high resolution quality, whereas rods may have good detection sensitivity but very poor resolution quality. So, and we have to remember that we can have cones functioning only at high light levels. And at high light levels, our pupil is always small. So we cannot have a big pupil and manage to have better image quality if we get rid of aberrations. There is a limit, and we have to realize that supervision, as it was thought some years ago, is not easily achieved. So how evaluate visual quality nowadays? As I said, there are some psychophysical measures. The simplest is the visual acuity, where we record resolution loss, and also contrast sensitivity, which gives us the advantage that we can record simultaneously resolution and contrast loss. We can compare this with some computational measures that have been advanced recently. These are the image metrics, which are some methods based on the ocular higher-order aberrations measured by the wavefront aberrometers. And this, as Harry Guinea saw before, some of these are modulation transfer function and point spread function. So visual acuity is the most widely used test for assessing the ocular integrity. And we all know that it forms an essential part of the routine examination in the everyday ophthalmological practice. It is used in the basic set of exams for evaluating ocular pathologic conditions. And actually, it's very important because it comprises one of the main criteria that define visual fitness for driving a vehicle and also visual readiness for many other occupations, such as for aircraft pilots. So visual acuity is based on the measurement of the minimum angle of resolution, which actually is the smallest angular separation at which 2 points can be resolved as 2 instead of 1. And the standard observer nowadays is defined one as having visual acuity that allowed him to identify letters with a stroke width of about 1 minute of arc. So a letter which has a total size of 5 minutes of arc is now this, the letter we call 6/6 letter or 20/20 letter. However, this is based on the observation of an astronomer, Robert Hooke, 250 years ago, who through his telescope realized that he needed to have 2 stars in 1 minute of arc separation in order to see them as 2. If we have a look at more recent data, some data by the group of Elliott et al. Some years ago, and who plotted visual acuity as a function of age. On this axis, visual acuity is depicted in logMAR units. On the right is more known as the Snellen visual acuity. You'll see that for ages of about 25 to 35 years old, the mean visual acuity is a lot better than 6/6 or 10/10, is about 6/4, which corresponds to 1.5 decimal units. And only when for older people, about 65, 70 years old, visual acuity is about 6/6. So you have to realize that the average visual acuity is not 6/6 as was supposed to be the standard, and it's a lot better than it. And we realize it every day in the practice. So the more traditional chart that was used all these years was the Snellen chart, which now is recognized that has some certain disadvantages. First of all, as you see, there are different number of letters for different lines. So for the top line, for someone to see and achieve a vision of 660, he only needs to see 1 letter to recognize 1 letter. However, for someone who needs to achieve a vision of 6/6, then he needs to see at least 5 or 6 letters in some other charts. So you understand that this is very crucial for low vision patients that have very low visual acuity. It's very crucial because only in 1 letter we can decide about their visual acuity. Second, because this difference of the different number of letters at different lines, there is a different crowding effect. And what crowding effect says is that it's more difficult to recognize a letter when it's between other letters. So you understand that this letter may be more difficult to see compared to a letter that is displayed on its own in a line. A third disadvantage, and very crucial one, is that the change in the letter size from line to line is not the same, is not equivalent. And this is very important, first of all, for statistics. From the moment the steps in visual acuity on the size of this letter is not different, you cannot take a mean of these measures, or you cannot calculate the standard deviation. So we need to have a chart with equivalent distances between these lines. And we also know that when we use Snellen chart, we usually use 1 chart for both eyes. So there is always a learning effect for the second eye. These disadvantages were recognized some years ago, 26 years ago, by ETDRS, and forced them to adopt a different chart as the standard one. This is the chart, the logMAR, as known today chart, which has been designed by the principles proposed by Belilovi and contains 10 letters that have been drawn by Sloan 40 years ago, which were chosen to be equally legible, although this is not the case, as we can see later. So what we have in this chart, we have 10 different letters, and each line has 5 letters, so the crowding effect is the same, and also the difference in the size between these letters is exactly 0.1 log step. So someone who has 660 vision, this corresponds to 1 logmar visual acuity. The 6.6 vision corresponds to 0, and someone who has better visual acuity than 6.6 then has negative values in logmar visual acuity. It's a bit, you may think that it's difficult to adopt, but it's not so difficult. I mean, it's something that can be learned throughout the day. And now, ETDRS acuity is considered to be the gold standard for clinical acuity measurements. However, there are some other disadvantages. I mean, in different countries, there are different logmar charts that they use. Before I show you a chart which uses letters. So what we have to do is identify letters. This one, as you always probably aware, is the Landolt C. And the Landolt C does not implicate exactly the same psychophysical measure. We don't have to identify a letter. We have to see a gap in this circle. So it's a different process. Also, you may be aware of the illiterate E, where again we don't have to identify, but we have to see the gap between this letter C to recognize the symbols. So you understand that visual acuity using different symbols may be differently recorded from one lab to another lab. Just I have this addend to see that there is also a logmar chart for students, and this is the Lee chart as recognized today. A small study that we did a couple of years ago in the university in Crete, we found that we recorded visual acuity using a logmar chart with letters and a logmar chart with Landolt C. And what we actually found is that the visual acuity was slightly higher, about 1.15 logmar units when we use letters. So you understand that this may show some difference between the 2 different charts used. A more recent study last year by Wittig in 2006 showed that this difference is more crucial when we use low vision patients. What this chart shows is the difference in visual acuity between the letters and the Landolt C as function of the visual acuity of the patients. And you can see for patients who had very low visual acuity, remember that this is a logmar scale, this difference was a lot. So for people who have low vision, it was a lot easier to identify letters than to see a gap in a Landolt C. Recently also we realized that the standard ETDRS chart that is used contains some characters, some Latin characters that are not readable by all European Union citizens. So we thought that we can construct a modified ETDRS chart that would compose a set of Sloan letters that would be readable by all citizens, people who use Latin alphabet, the Cyrillic alphabet, and the Greek alphabet. And what we had to do is to replace some of the letters from the Latin alphabet with some letters that also are in the Latin alphabet, but are also parts of the Cyrillic and the Greek alphabet. And we constructed a chart like this. We proved that in a work that there was no statistical difference by measuring visual acuity with the standard ETDRS chart and with this new modified ETDRS chart. Another factor that I posed before also, when we measure visual acuity, is the choice of letters. And by using some psychophysical techniques and displaying letters on the monitor and then measuring their identification threshold, we found that some letters are a lot more difficult to read, to identify than some others. In this graph, the logmar visual acuity is plotted as a function of letters, and you see as we go up in this graph, it's more difficult to identify a letter, and you see the most difficult letter was letter B, C, and K. On the other hand, letters A, P, V are very easy to identify. You realize that the letters are very close to this line, which is the average line, are the ideal one to be used in one chart because they don't show difference between each other. So that was about far visual acuity. I'll have only 2-3 slides about near visual acuity because today is becoming more important as we use it to evaluate visual performance after cataract surgery, but also after refractive surgery and monovision. And we have to realize that reading now vision statements, reading visual acuity today is limited to qualitative measures. And why do I say qualitative? Because what we record is the size of the letter only, but not for a standard distance. And we may not know that the standard test that used in most of the laboratories and clinics, the Jaeger test, has no numerical meaning, and the numbers we see in the Jaeger from 1 to 6 refer to item numbers in a print catalog in 1856, nothing more than this. So there's some work recently been done to use some modified near visual acuity charts, like this one, the Rosenbaum Pocket Vision Screener, where it has numbers and also some other symbols. But again, as I said, this one may have different identification thresholds between each other, so may not pose the ideal situation to record visual acuity. Very recently, ETDRS realized also that there was a gap there for near visual acuity. So what it did, it actually reconstructed a chart for near visual acuity that now has been used at 40 centimeter distance, and again has a logmar scale, in logmar scale. However, this may not leave all of us satisfied, because if this chart has to be used, as I said, at 40 centimeter distance, and 40 centimeter distance is not a near distance that we usually use when reading a newspaper, neither the intermediate distance when we use a computer screen. So it's not the ideal situation. So we thought to construct again a new near visual acuity chart that first of all would be composed of letters readable by all European Union citizens, and also would have the choice to use the same chart and record visual acuity at 2 different distances, at 33 centimeters at near and at 66 centimeters, which we thought would be the intermediate distance. And you can use the same chart for recording visual acuity for both distances, and the values are here for the 33 centimeters and on the right side for the 66 centimeter recordings. Now, this was about visual acuity, and as I said also in the beginning, the image of the letter on the retina is not only on the photoreceptors, is never sharp. It's always a bit blurred because of the ocular higher order aberrations and of the scatter. And as you see, a simulated letter may look like this. You see there is not only a resolution loss of this letter, but also a contrast loss on the retina. And also, so contrast is very important to measure, but how we should measure it? If we have a look at a picture of a carpenter scene, where we see an everyday situation, and we take a line across this picture, we see that there are many changes in luminance in this picture. In some cases, it's very, very quick changes. So there's a lot of the detail here. In some other changes are not so, there is not a lot of detail, like the boundaries of this building. But we can see that these scenes in the real world are delineated from another by changes in contrast. And an important factor seems to be spatial frequency, which actually is the detail we get from a screen. Here is a lot of high detail, maybe here is a lower detail. So how we evaluate contrastivity in the lab is we use a high resolution monitor for the projection of visual stimuli. We need to have a stimulus generator card for developing the stimuli, a software for developing and finding the threshold, where the sensitivity will be evaluated, and also a lot of patience. And we usually use vertical gratings like this, where luminance is modulated on the horizontal direction. So we have white and dark bars. And we usually plot contrastivity in a chart like this. Here is the contrastivity, which is actually the reciprocal of the threshold we measure. So as we go up, it's lower the sensitivity, higher the sensitivity we achieve, lower the contrast. And usually on the x-axis, we have the spatial frequency. Just to remind you, on the left, we have low spatial frequency gratings, and on the right, high special frequency gratings. And we start recording for different special frequencies, and at the end we get a curve like this. So what this curve says is that we have the maximum contrast at about middle special frequencies, about 4 to 6 cycles per degrees, but also by extending this line and finding the cutoff frequency in this x-axis, we can find and evaluate the resolution of this in cycle per degrees. So the cutoff frequency usually of normals is about 30 to 45 cycles per degrees, and this corresponds very well with visual acuity, where because 30 cycles per degrees is about 6.6 visual acuity, 45 is 6.4 visual acuity. And why does the contrastivity function has this form? I will not go through this a lot, but it has been known now for many years, since Hubel and Wiesel got the Nobel Prize in 1959, that visual cortical neurons respond to Siebel gratings. So we can say that this contrastivity curve we have is an envelope of many narrowly tuned special frequencies, narrowly tuned cortical neurons, and this is the resulting curve we get. And what each set of neurons, group of neurons give us in image quality, you see that for low special frequencies give us a lot of contrast because we have high contrastivity here. And then as we go to higher special frequency, the contrast may be, probably you will not be able to see it very well this, but what we get from high special frequencies is the edges and not any more contrast. The sum of all these channels give us a nice image. And you can see here, we can simulate again the importance of these frequencies. Here is an original image. If we take out the high special frequency, with only the low and the medium special frequencies will look like this. You see, we still can see the face, but if the high special frequencies give us a lot of detail about the edge of the face, so the sum of these two will give us a sharper image. Now, how do we usually evaluate? This is how we would ideally evaluate contrastivity in the lab, but how do we evaluate contrastivity in a clinic? I mean, you probably came across the low contrastivity DRS chart, but we have to understand that this does not measure contrastivity. What it measures is visual acuity at low contrast. So again, we measure resolution and not contrastivity for low contrast targets. Another way is to use a Pellier-Robson chart, which also is a standard chart. But again, here we don't measure resolution because we use the same size of the letters. So what we actually measure is only contrast. And there are also some other charts that have been devised. This is the chart devised by Vistek, where actually the patient has to look at 4 different special frequencies and has to all the time to answer and say at which circle the grating is plotted. You have to realize that, first of all, there is about 50% chance to find the correct answer. So it's a lot of guessing here. We only record 4 special frequencies, and sometimes higher special frequencies are very important to record, and also not many contrast levels. So these are some disadvantages. The functional acuity contrast test is another one, which now use 5 special frequencies across here. And instead of having a circle with blank and gratings there, it has a grating at vertical orientation and tilted slightly on the left and on the right. So now you have 33% of chances to find the correct grating. And it's slightly more accurate than the previous one, but again, there are some certain disadvantages. A very important disadvantage of this chart, according to what I've seen today, is that usually when we record the contrastivity, pupil size or lighting levels are not controlled, and these are very important. The luminance of the chart is not homogeneous, and it wears out very quickly with time. There is a limited range of special frequencies. We can go up to 12 cycles per degrees, which corresponds to 615 in visual acuity, so we don't see high special frequency sensitivity. There is a limited contrast step, and also, as I said, there is a high possibility of guessing. No. Why is it important to evaluate contrastivity? I mean, this is very crude again here, but I don't have time to go into this. If A is supposed to be the ideal contrastivity function, we can see that under conditions of low refractive error, for example, what we would get would be a curve like the one with D. And what it happens is that they will have a decreased sensitivity for high special frequencies. That's the reason I said that high special frequencies are very important to be recorded most of the times. Now, if we have a high refractive error, or in the case of amblyopia, we will get a line like this usually. So you see both medium and high and intermediate special frequencies are affected. In the cases of aging, where we have degeneration in the visual pathways, it has been shown recently that we may have a decrease mostly in the low special frequencies than compared to the high special frequencies. So there is a differentiation in high special frequency in different diseases. So it's very important, its evaluation. And I will finish with a couple of data collected in our lab. First of all, we try to measure the impact of higher order aberrations on contrastivity. And what this graph shows actually is we recorded wavefront aberration in about 250 eyes, and we found the variability in the higher order aberrations in these eyes. And you see that most of the eyes show an RMS error of about 0.3 micrometers, but there are some eyes that show very high magnitudes of higher order aberrations, and some eyes show very low magnitude of higher order aberrations. If we try to convert this by using some formula in spherical equivalent, you see that on average the impact of higher order aberrations is less than a quarter of a diopter, is about 1/8 of a diopter. And only in some eyes there is the higher order aberration may have a big impact, a large impact on visual quality. And as we can simulate by using the point strength function, for example, at 3 millimeters, a point on the retina may be a point, so there is no effect from higher order aberrations. At 6 millimeters, though, when the pupil size is larger, then we can see that point strength function is worse. So also the simulated image on the retina would look like this, having less resolution and less contrast. Similarly, modulation transfer function is affected. In a diffraction limited system that would have no aberrations, the modulation transfer function would be higher and better at 6 millimeter pupils than 3 millimeter pupils. But in the real case, in our eye, due to the higher order aberration, at 6 millimeter pupil, the modulation transfer function is reduced a lot compared to the 3 millimeter pupil. But these are all theoretical measures, computational measures from the wavefront aberrations. We tried to record also contrastivity. There were a couple of things that we had to check first. I think this is recording contrastivity at 3 millimeters to contrastivity at 6 millimeters. First of all, we would have a different effect of luminance. You understand that at 60 millimeter pupil, there is 4 times more luminance getting into the eye. So we would expect to have better contrastivity. So what we did is we used filters to take out this effect and have the same retinal illuminance on the retina by recording contrastivity for 2 different pupil sizes, at 3 millimeter and 6 millimeter. And here is the 2 curves we got. At 6 millimeter, due to higher order aberration probably, there is a decrease in contrast sensitivity. And if we plot the difference of these 2 curves as a function of the special frequency, you'll see that this is more for high special frequencies. As I saw before, similar to what happens in low refractive error. And you may think that this is not a big difference, but this difference is about 6 dBs, and this is about 50% contrast. So there is a decrease in contrast about 50% due to the higher order aberrations. Also, we recorded contrastivity following refractive surgery. And before we started this, we did this study, we thought that we have to concentrate on which factors may affect, first of all, quality of vision. And of course, first of all, maybe residual refractive error. And this is very important because most of the studies after refractive surgery, what they record is visual acuity or contrastivity with the best spectral correction, but this is not the case for the patient when it's outside in real life. Also, there may be induced higher order aberrations, especially spherical aberrations due to the laser. And also some surface from corneal some scatter, from corneal irregularities as happens especially in PRK. So in the past, there was some color-correcting data. Usually, they recorded the contrastivity by using the charts that I showed you before. Some recent studies showed that there is a depression in contrastivity after refractive surgery at the first month, and then contrastivity comes back at about 6 months post-operatively. And they also, some studies showed that better results for customized ablation. So when the ablations corrected not only the spherocylindrical refractive error, but also the higher order aberrations. Now, in our study, we recorded contrastivity, but at the same time, we recorded aberrations, higher order aberrations. And these are the groups. We took 2 groups of 12 patients each from a LASIK and PRK. And this is the higher order aberrations preoperatively. At 1 month, we see that there's a decrease in higher order aberrations more than twice. And there is a slight decrease at 3 months. But higher order aberrations definitely increase following refractive surgery. And these are probably mainly due to spherical aberration. Now, we recorded also contrastivity, and what we found is, you see, preoperatively, contrastivity was the green line, and then at 1 month, there was a depression of about 3 dBs, which is to 30% of contrast, but at 3 months, contrastivity was the same. So, but this was with the best spectral corrected lenses. When we did the same by using unaided vision, then we found that there is definitely a decrease in contrastivity, which is mainly due to the residual refractive error and not the higher order aberrations. So to conclude, first of all, visual acuity has to be measured in a standardized manner in order to use the data for research and clinical protocols. We have to stress that there is no standardized quantitative method for evaluating near visual performance, and we have to take care about this. That contrastivity offers a more complete investigation of the integrity of the visual system because sample visual deficiencies can be detected. That ocular higher order aberration adversely affect contrastivity function, particularly at high special frequencies. But the increased higher order aberrations following refractive surgery do not seem to compromise contrastivity. Thank you for your attention.
Thank you very much for the contribution. I would like to invite now questions for the last 2 talks. And if there are no questions, we're going to have the break till 11 o'clock for part 2.